friends, welcome to 7th session on numerical analysis of BSc 5th semester. In this session, I will explain you about the errors in the evaluation of the function f of x1, x2, xn. So let us have the recap of the previous session. In the previous session, we have learned about the error associated with the computation of the number of the form x to the power n. And we have solved a couple of examples related to that topic. In this session, we will be discussing about what is the error associated in the computation of the function of the form f of x1, x2, xn. So let us start the discussion. If x is a function, try to understand, capital X here is the function given to us. Capital X, we are taking it as a function of several independent variables, x1, x2, small x1, small x2, small x3, small xn. These are the independent variables of the function capital X. So now if delta x is the error in the capital X, see, delta x is the error which is associated with the error in the function capital X, because there will be an error in the variables small x1, small x2, small xn. We know that when capital X is a function depending on small x1, small x2 and small xn, when there is a change in the variables x1, x2, xn, there will be a corresponding change in the function capital X. Likewise, if there is an error associated with these variables small x1, small x2, small xn, then there will be an error in the function capital X. So that's what we are saying here. Capital X is having an error delta x because of the errors small delta of small x1, delta small x2, delta small xn, which is present in the variables x1, x2 and xn respectively. Now we can write x plus delta x as f of x1 plus delta x1, x2 plus delta x2, xn plus delta xn. This is quite trivial, because when x is f of x1, x2, xn, x plus delta x will be f of x1 plus delta x1, x2 plus delta x2 and so on. Now we can expand this using the Taylor series. So we know the Taylor series expansion for the function of several independent variables. So that we are using over here. This is an important step. Please try to remember this. So we are expanding this function x plus delta x, which is written like this. This we are expanding using the Taylor series. So when we expand it in the Taylor series, it looks like this. Now here plus dot has been written, because afterwards also there will be terms with higher powers of delta x1, delta x2, delta xn present. But since the errors are small, delta x1, delta x2, delta xn are small, the small number to the power 2, small number to the power 3 will be still smaller. Therefore, we can neglect the terms with higher powers in delta x1, delta x2, delta xn, and therefore these terms, the terms after this particular thing can be omitted, so that we can have only these things contributing towards the final answer. Now we can see delta x is equal to, capital X is nothing but f of x1, x2, xn, and here also the same thing. So we can cancel del x with this thing, because these two are same. You can see here from the definition. So when you take it to that side, it will become minus. So plus and minus of the same quantity cancels out. So only thing remaining will be delta x equal to this bracket. So that is visible here. Now the relative error. Now the relative error in capital X can be written as delta x divided by x, because we know that delta x is the error associated with capital X. That is the absolute error. Absolute error divided by the value of the function, that gives us the relative error. So therefore delta x divided by x, that we are writing over here. Everywhere we are having delta x value is here in this step. Keeping this value in the numerator divided by capital X and then separate division, that gives us this particular thing on the right hand side of the relative error. Now we are using one important thing. And what is that important thing? I will show you. Principle of equal effects we are going to use. So what is meant by principle of equal effects? Here in this particular step, we have written the RHS like this. Here there are terms with delta x1 into dou x by dou x1, delta x2 into dou x by dou x2, like that. We are writing here that each of such quantities are contributing equal effect on the total result. Therefore, we can write that these effects are equal. Delta x1 dou x by dou x1 is equal to delta x2. This is equal to this is equal to the next one, and so on. Each things will be equal. That we are writing. So this is by the principle of equal effects. When we write like this, in this expression, this becomes same as this becomes same as this. So each term in the relative error, the first term itself will be repeating n times. That's what we have written here. This first term has been written n times. Now therefore delta x is equal to n times of the first term. That we have written over here. Delta x is equal to n times of the first term. So that is here in this particular step. Delta x is equal to n times of the first term, or you can say that n times of the second term, or you can say that n times of the nth term, no problem. So we are considering nth times of the delta x equal to n times of delta small x1, partial derivative of capital X with respect to small x1, that we have used here. And by using that we can compute, see we know the absolute error in the given function. When we know the absolute error in the given function, we can compute the absolute error in the variable x1 by using the same expression. Keeping this as it is, we can transfer it to the other side. We get this formula. We get this particular formula. So now by using this formula, we can get the error associated with the first variable by knowing the total error in the given function. So that we should know. If we know that, we can compute the error associated with the first variable. On the other hand, if we know the error associated with the variables involved, we can compute the error associated with the given function using this formula directly. If we use this formula, we can compute the error associated with the given function. What we should have in this case? We should have to know error associated with each variable involved. On the other hand, when we know the error associated with the total function, we can use that by the simply modified expression, and we can compute the error associated with each such variables which constitute the given function. So likewise, we can have delta x2 also, the same type formula. Wherever x1 is there, x2 is coming, that's all. N stands for the number of variables. So we shall use these expressions to solve the problems, and we are having very interesting discussion now, that is on worked example. So let us move on to the worked examples. So here is the first question. Please have a look at this. So what is there in this question? The error in the measurement of the area of the cross section of a rod is desired to be 0.2%. So what has been given? Percentage error has been given. Percentage error of the area of the cross section of a rod has been given to us. We have to find out how accurately should the diameter of that rod be measured. So we have to find out this question. Now, start the solution. Suppose that small d is the diameter of the cross section of a rod. We assume that rod is circular. When rod is, that is the cross section of the rod is circular. When the cross section of the rod is circular and d is the diameter, area of the cross section of the rod is simple. That is the standard formula. We know the area of circle is pi r square, that is okay, pi r square. Now when r is half of d, so in place of r, if we write d by 2, and r square is nothing but d square by 2 square, that is d square by 4. This is the thing over here. You can look at this. Therefore area of the cross section of the rod is pi d square by 4. This is the area we have now in our hand. What we can understand from this? Area is a function of d. How many variables? Only one variable. N here is 1. A is a function of d because pi is a constant, 4 is a constant. So area is a function of d, one variable. Now what has been given to us? It is given to us the percentage error in A is 0.2. You look at the question here. Percentage error, that is 0.2%. That means percentage error is 0.2. We should write like this. Percentage error in A is 0.2. That implies, what is the definition of percentage error? Percentage error is relative error into 100. What is relative error? Error in A divided by A, that is relative error. Relative error into 100, that is percentage error. So LHS has been written like this, and on RHS we are having 0.2 as it is. Now keeping this delta A as it is on LHS, taking the other quantities to the right hand side, we get this expression. Now if we simplify, 0.2 divided by 100 means 0.002. Two more zeros are coming over here in between point and 2. So we are having 0.002 into A. A value is pi d square by 4. Now we know that A is a function of d, single independent variable. That implies delta d. We have seen the formula, we have seen in the previous step. Delta x1 is equal to delta capital X divided by n into partial derivative of capital X with respect to x1. Here x1 is d, capital X is A. Therefore delta d is nothing but delta of A divided by n, here is 1 because number of independent variables is 1, into partial derivative of the function with respect to the independent variable d. So it is the thing we are having. Now if we simplify, what is the value of dou A by dou t? We know that A is this thing. We know that A is this thing. A is pi d square by 4. If you differentiate partially A with respect to d, if you differentiate A partially with respect to d, pi by 4 remains constant, d square becomes 2d. So 2 ones are 2 twos are. So pi by 2 into d it remains. So that is over here, pi by 2 into d. Dou A by dou that is a partial derivative of a with respect to d is written over here. You can look at this. So this is the value, we can substitute it here. Then what happens, let us see. Okay, now if you look at this value, when we substitute it here in the formula which is above here, now in this place, what happens? Delta D is equal to, what is delta A? Delta A is, it is available here, 0.02 into pi d square by 4. This we have substituted, whole divided by, actually it is whole divided by, this is in the numerator, whole divided by the value of this we have computed pi d by 2, that is available here. So if you simplify this, you will get 0.01 into d, 0.01 into d. Now let us take this to the other side. So error in d divided by d, that becomes the relative error in d. So relative error in d is equal to, only the thing remaining on RHS is 0.001. So that is here. Now to calculate the percentage error, relative error is to be multiplied with 100. So relative error multiplied by 100, that gives us the percentage error in d. Percentage error in d is, this value is 0.001 into 100. If you simplify this, the answer is going to be 0.1. So percentage error in d will be 0.1. So what can we conclude? We can conclude that diameter is measured to an accuracy of 0.1%, because the error associated with the percentage error associated with d is 0.1. That means the diameter is measured with a percentage error of 0.1. That means that diameter is measured to an accuracy of 0.1. So this completes the solution of the first example. Now let us have one more example for your better understanding. Okay, now I will show you another example and I will explain you how it can be solved. Now here is the question. Two sides and included angle. See, two sides have been given and this angle has been given of a triangular park. See, park is there which is triangle shape, and how what are the values? Two sides are 96 feet and 87 feet respectively, and the included angle, that angle, included angle means angle made by those two sides, that is 36 degree. We have to find the allowable errors in these two quantities in order that the area of the park may be determined to the nearest square foot. Area is always measured in terms of square units. Here the units are foot. Therefore, the area is square feet, and total area whatever we get, that is to be rounded to the nearest square foot. That is the error in the total area, and we have to find out what are the possible errors in the two sides and one angle. That we have to do. Okay, let's start the solution. Now here, what is the given thing? Park is triangle. This is the given data, and assume that park is triangle ABC like this. So park has been assumed as triangle ABC. Now if alpha is the area, I am not using capital A because capital A has already been taken over here. Let us use alpha for the representation of area. So area of the triangular park is alpha. Then area of triangle is given with several formulae. When two sides and included angle is known, then one of the important formula of area of the triangle is 1/2 into those two sides into sine of the included angle. So half into BC sine A. B stands for this is B stands for one side, C stands for another side, and A is the included angle. So that we have to consider. So 1 by 2 as it is, B value we have substituted one side, another side into sine of the angle between them. So use the calculator, find out the answer. You will get the answer to be 2454.59 square foot. And now what has been given to us, the area is determined to the nearest square foot. We have to round off this number to the nearest square foot. So when you round off this number to the nearest square foot, how it can be done, you please see. We want to stop here because nearest square foot means we don't want to have any decimal place. We have to stop here. Now we have to look at its next digit. It is 5. 5, when it is there, we have to look at the number at which we want to stop. If it is to be increased by 1. If it is even, it is to be increased by 1. So it is to be made as 2455. So that is over here, 2455 square foot. So that is the area of the triangle after rounding off. Now if we do this, what is the error associated with this calculation? We have one important concept which we have studied very well in the section of valid significant figures. There we have explained that the maximum error in the evaluation of such number is always equal to 1 by 2 into unit of the last digit. So what is the last digit here? The last digit is this thing, 5. 5 is the last digit. What is its unit? It is having the unit. You look at the places. This is the units place, tens place, 100 place, 1000 place. So unit of this is nothing but 1. So that can be written as 10 to the power 0. So it is 1. 1 by 2 into 1 is 1 by 2. So therefore delta A is 0.5. That we are having over here. Now, so delta A, error in area, we have computed it as 0.5. Now we know that area is a function of two sides and an angle. Therefore, we can have delta B equals to delta A divided by 3 is n here. We are directly writing this from the formula. N is 3 and partial derivative of the first variable A with respect to the first variable, and if we substitute the values, we get this as delta B. Delta B is this thing. This simplification is simple. You can do it by yourself. And similarly, delta C, the second variable, the total error divided by partial derivative of A with respect to the second variable. Substitute the values and simplify. You will get the answer this much. And similarly, delta A, that is the third variable, A, angle. It is also delta alpha, that is the total error, that is 0.5. Just now we have computed 3 into partial derivative of alpha with respect to A, and that is here cos A. You look at this, how we have computed dou alpha by dou A by using the expression of alpha. What is alpha? Alpha is here 1 by 2 BC into sin A. By using this formula, by partially differentiating it with respect to the variables, we can get dou alpha by dou B, dou alpha by dou C, dou alpha by dou A, like that. So after substituting the values and simplifying, we get the error in the third variable. So this is how one can solve the problems by looking at the error associated with the given functions. And I hope you understood very well. With this, let me stop here, and we have a couple of questions to be answered. You please try to answer this question when you are free, and with this, let me stop. Thank you very much.